files were uploaded to YouTube, and so if you went to YouTube and didn't find the video that you were looking for, I'm going to be going back through that this afternoon to make sure that it's all correct. Other announcements is, so homework 2 is available now on Blackboard. And for that one assignment, I'm going to push the submission deadline from the usual 1 o'clock submission to 11:59 on Friday. And the reason for that is to provide one additional opportunity for us to discuss the homework assignment in class on Friday. So I wanted to point out that I'd made that change in Blackboard, that the assignment's there and it's not due until effectively just before midnight on Friday. And then Monday of next week, we're going to have our first quiz. It'll just be a relatively low stakes, very brief quiz. I expect it will take probably 10 or 15 minutes for that. And then Wednesday of next week, we'll have an assignment that's related to reactors. And so kinetics and reactors go hand in hand. That one will be due back at the usual time of 1 p.m. Does anybody have any announcement-related questions? All right. So the kinetics that we're talking about today apply both to chemicals and to biological systems. The idea of zero order, first order, second order kinetics. And what we need to do is connect the idea of changing amounts and reaction rates to how concentrations change over time, and then in a lecture to come pretty soon, we're going to talk about the location that different types of reactions can occur. So remember that in our previous conversations about zero order reactions, we talked about it in terms of the amount of something. So the change in the amount over time. And concentration and amount are effectively the same thing. It's just that we're talking about, in terms of concentration, we're talking about the amount of something within a certain volume. And so if we're talking about the milligrams of some constituent per liter of volume, then we're talking in terms of concentration. But we have the same reaction rate constant K, whether we're talking about the change of something in absolute amount terms or in terms of concentration. The reaction rate constant's not any different if we're talking about amount versus concentration. So what we need is an equation that will allow us to predict what is going to be the concentration at some time. And if we integrate the changing concentration with respect to time, and on the right-hand side of the equation, integrate the rate constant from the beginning of time through some certain time t that we're interested in knowing what's the concentration at time t. That's where we get this equation that tells us that the concentration at time t is the initial concentration C naught plus the rate constant times how much time has elapsed. So if we have a production reaction in zero order kinetics, then we'll have a positive K. And if it's a reaction where some constituent is decreasing in concentration over time, then we'd have a negative K value for that. Okay, so let's take a look at the in-class exercise that I gave you, problem 1. And hopefully you saw my email about bringing your computer if you had it available. But let me bring up the in-class exercise on the screen here so that it's captured in the recording. For problem 1, we're going to be dealing with zero order kinetics, and we want to graph this just to get a sense for what is the rate constant. So we have this observed data of nitrogen gas stripping oxygen from water before an aeration test is performed. So what we're doing in this is we have some sample of water and a bubbling stone at the bottom of it connected to a tube, and there's nitrogen gas that we're flushing the oxygen out of the water by saturating the water with nitrogen. So the rate of that is given as zero order. It's zero order kinetics. We're going to take this data and put it into Excel and then find out from a best fit line what's the rate constant, and then use the rate constant to find out how long it would take for the concentration to be down as low as 0.5 milligrams per liter. So you can see that's beyond the 90 seconds that we have experimental data for. We're starting with the dissolved oxygen concentration at the beginning was 9.5, and then it's gradually going down. So let's put that into Excel, starting with time in seconds and then concentration in milligrams per liter. Hopefully, if you're not following along on your own computer, then you can either watch mine or hover over somebody you're sitting next to. So 5, 15, 30, 45, 60, and 90. So it's not always 15-second increments here. Since we're doing a scatter plot, it doesn't have to always be the 15-second increments. 9.5, 8.375. 7.25, 6.125, 5, and 2.75. Now, when I made this example, I don't remember if I made it perfectly fitting a linear process or if there's going to be a little bit of noise and scatter in there. But we've got our data table here, and for part A, it says use Microsoft Excel to graph concentration versus time. So what we're going to put is concentration on the vertical axis and time on the horizontal axis. So I sometimes get mixed results when you just highlight the data and tell it to make a graph. Sometimes that works, but not always. What we want is a scatter plot. So here under charts, we just only want the data. We don't want it to be like connecting the dots. We'll put in a regression line. So we just want the data itself. So let's take a look at what we have. It looks like it did, in fact, put the time on the horizontal axis and the concentration on the vertical axis. But just as a matter of habit, we should add the axis labels. So do that here. Once you've selected the graph, plus and add the axis titles. So then we're going to add on the horizontal axis, it's time in seconds. And then the vertical axis, we'll have it concentration in milligrams per liter. Okay. Now you'll notice it has these grid markings. That's the grid markings. It's not going to benefit us in any way with the linear regression that we're doing, and maybe it makes it visually a little bit more busy. So what we can do is just delete them. If you click on one of the grid lines and press the delete button, we can make those go away. Just makes it a little bit more clean here. All right. So far we've just graphed the data. The question is, what's the rate constant? And in part B, that's what we're going to do here, is add a best fit line to the data to find the rate constant K. Okay, so right click on one of the data points and then add trend line. And it gives us some options here: exponential, logarithmic, polynomial, power. In our case, it defaulted to linear, and that seems to be describing the data pretty well. We knew from the problem statement it said it's zero order kinetics, which should be linear when you're graphing time versus concentration. So that further reinforces that we ought to go with linear. But let's just have it display the equation on the chart, because we need that to get the K value, the equation. Oops. So here's our equation. And then it's always fun to look at the R value to see how well the data fits the linear regression here. So format trend line. Let me also have it display the R squared. 1. I should have added some scatter to the data so it wasn't perfect. The real world, you're never going to be measuring things and have it perfectly linear. Sometimes it'll be pretty close, but it'll never be perfectly linear. But in this case, so we want to use the best fit line to find the rate constant K. So in a zero-order reaction, a consumption reaction has a negative K. So for us, K is negative 0.075. So K is negative 0.075. And if you look at the type of the equation that's going to go into here, we're going to multiply K by time, and then it's going to give us units of concentration in milligrams per liter. So then what's the units of K? If we want to multiply it by time, and it gives it milligrams per liter, so it is milligrams per liter and then seconds in the denominator. Because once we multiply K by seconds in time, then we want K to have units of milligrams per liter in order for us to be able to add it to the initial concentration. So let me just write here, K equals negative 0.075 milligrams per liter times second. Insert symbol dot. Where's that dot symbol? Mathematical operators, maybe. We'll spend all of class doing this. Number like, no. There it is, dot. Times seconds. Oh. Okay. So K is 0.075 milligrams per liter seconds. So we've now done part A and B. Now, part C. Use this formula to determine the time required until oxygen concentration is 0.5 milligrams per liter. So what we're saying is the initial concentration of oxygen in the water was 9.5 milligrams per liter. And the concentration at T equals unknown is what we're trying to find. You know, what is the time? 0.5 milligrams per liter. Okay, so we know C naught. We know C sub T, that's this one. Just C at some time. That's the 0.5 on the left-hand side of the equation. We know K. Solve for T. So let me pause for a moment, give you a chance to solve for T. Is it 120 seconds? Okay. So just to reevaluate here, the initial concentration was 9.5. We're bubbling nitrogen through that liquid. It's stripping out the dissolved oxygen at a constant rate, meaning the amount of oxygen which is in the water does not affect the rate at which it is being stripped out. The rate at which it is being stripped out is driven by the rate that we are applying nitrogen to the water. That's what determines how quickly this loss occurs. So we rearrange the zero-order kinetics reaction to solve for T, 120 seconds. All right, we did it. So that's problem one. Zero-order kinetics. Any questions about that before we move on to first-order reactions? Okay, so what we learned previously about first-order reactions is that the rate of the reaction is influenced by the amount of the constituent that's present. So, for example, in a production reaction, the more of the product you have, the faster the reaction is going to go. Or as the amount of the reactant decreases, the rate of the reaction decreases. So either of those can be true depending on whether it's a production or consumption reaction. But the point is, the rate is the constant times the concentration. So at the start of the reaction, so at time 0, then the concentration is some initial quantity, C naught. And what we also talked about previously about first order reactions is that we can find out the constant K by graphing the amount on the vertical axis having been put through the logarithm function and the time on the horizontal axis. So if we integrate this expression that the change in concentration over time is K times C, then that gives us a slightly different formula relating the concentration at a given time to the initial concentration. So it's not linear behavior. The logarithm is what helps us to account for the fact that the amount is influencing the rate of the reaction. We could rearrange that to say that the concentration at some time is the initial concentration times e to the kt. So K in a first order reaction is going to have different units than in a zero order reaction. In this zero order reaction that we just looked at, K had units of mass per volume time. But what will be the units of K in this first order reaction? If we put it into E, the exponent should be unitless. So K times T should be unitless.
1 over seconds.
That means that T is going to be 1 over seconds, 1 over time. Whether it's minutes, hours, days, years, it's going to be inverse time. So again, K is positive if it's a production reaction and negative if it's a consumption reaction. So let's take a look at one of those here with example number 2. We're removing a pollutant from water. Here's our data that describes it, and let's determine whether the kinetics are zero order or first order. Well, we should just be able to, maybe by looking at it, already know that it's not zero order. Look at from 0 to 12, you lost 30 milligrams per liter. It went from 220 to 190 from 0 to 12 in a 12-hour increment. But in the next 12 hours, it went from 190 to 170, which is a loss of 20. So it went from a loss of 30 to a loss of 20. So that's not linear. So we know it's not first order, excuse me, we know it's not zero order. It is first order. Let's just prove it to ourselves by graphing it. So let me create a new sheet here. Let's just type in the data so that we've got that available. Time, units of hours, and concentration, milligrams per liter. So 0, 12, 24, 48, 96, and 144. Okay, so it starts at 220, 190, 170, 130, 75, and 45. Okay, so the way that we're going to determine the kinetics is graph the data both ways, either just the first way, which is we're going to tell it to do a graph like we did before. That does not appear to be linear. This would be, if it was first order kinetics, then we would have time versus amount, and that's clearly not linear. How do we know? Let's just add the trend line there and see if we make it linear. What's the r squared? 0.96. But what if we do the logarithm of the amount? So we need that column, ln of concentration. Okay. So let's add a column that gives us the ln of the concentration. And do it to all of them. And then let's just make another chart. So this time I'm going to insert, well, I guess I could just try highlighting what I want graphed. So time and concentration. Let's see if Excel figures it out. So chart Scatter. Yeah, seems like it did okay. Let's add the labels though. Axis titles. So on the horizontal axis, we've got time in hours. And on the vertical axis, we've got Ln of concentration in terms of milligrams per liter. So you'll notice I did the parentheses to say the logarithm of the concentration, but then I did these brackets to define the units, just to differentiate between what was a function and what was the units. Let's put in the scatter. So, we'll delete these grid lines that aren't helping us at all. Right-click on the data point, add trend line. Let's display the equation and also the r squared. Okay, the r squared is better than it was for the linear. So I'd say that first order kinetics describes this data better than zero order kinetics. So I'm going to say this is first order kinetics. Now, what's the k value? It says 0.011. Maybe I want more precision than that. Let me have it see. Let me see if I can display more digits there. So right-click, format trend line label, number, and have it be three number places. Let's see. How about more than that? I want 5. Okay. So 0.01104. So don't just take like the default precision that it gives you necessarily. You can control that. The way I got to that is I right-clicked. Well, maybe you just click on the trend line label itself. And then here under the label options, change the category. I think it might have said general to begin with. I told it number, and then if it's number, you can choose how many decimal places are displayed. So for this example, then our k value we get from the slope of the trend line, and this negative sign is part of the k value. So we do need to pay note of the k is negative 0.01104, and then the units are going to be hours to the -1. Okay, so we got the rate constant. Now, part C is asking how long will it take for the pollutant concentration to equal 30 milligrams per liter? All right, so here's our equation. We'll use this one for part C. So part C, we'll use this one for part C. It's just rearranged more conveniently for us if we are solving for time. So basically T is equal to the logarithm of C divided by C naught divided by K. So we're rearranging. All right, so let me give you a moment to find out how long is it going to take for the pollutant concentration to go from 220 down to 30. Did you get 180 hours? 181 hours? Here I hadn't shown the full K value. I've got a more precise K value when I say 0.01104, then that tells me that the time is 180.5 hours. If I hadn't gone for that extra precision in the K value and just went with 0.011, then it says 181. But you get the idea on how we use this equation to predict the concentration over time for first order kinetics. And by the way, what's first order kinetics? That's when the reaction is influenced by the amount that's present. Okay, and this is a pollutant being removed from wastewater. Oh, from water. Guess it could be wastewater. We're removing a pollutant from water. Okay, part D. What will be the pollutant concentration after 5 days? So that's saying, assuming that this is the start of time, when the concentration was 220, that's the start. And we want to know if T equals 5 days, so how many hours is that? I guess we'd have to multiply it by 24 to get the right amount of hours. Because our K value has units of hours, we can't put in days for T if our K value has units of inverse hours. So do part D. Predict what will be the concentration after 5 days. Okay, 5 days is 120 hours. So if this is continuing to consume the pollutant following the same kinetics, then it's starting off as 220 milligrams per liter, and it's going to finish at 58.8 milligrams per liter after 5 days. So the rate of it breaking it down is slowing down as there's less present. Like if this was, for example, bacteria consuming a pollutant, it's their substrate, meaning it's their food, they're going to slow down in how quickly they can consume the substrate when there's less of it available. So that's like a real world example of what causes first order kinetics, is if it's a microbial reaction, then the rate of breakdown decreases when the amount decreases. Any questions about first order kinetics and how to calculate concentrations over time? So this form of the equation is useful if you are solving for T. And this form of the equation is useful if you're solving for concentration. And of course we know that it's just basically the inverse, that e to the kt, e and logarithm are related to each other. So that's first order reactions. Yes?
Can you go back to the Excel where you were comparing the two graphs?
Yeah.
So for the, not the natural log or the concentration, but this one,
Mm-hmm.
which one did you choose? Like linear or exponential or?
Yeah, so this was just a graph of time versus concentration. And when you do that, it's not like the data points are completely far away from a linear trend. Like they're kind of in the vicinity of that linear trend. So the R squared of 0.96, it's pretty high, but it's not as good as this one where it was 0.999. So that's why we ended up saying that this is first order kinetics, is because the R squared value was a better fit.
So could you find the K if you did like an exponential function?
Like if you just say, let's not make it a linear graph. Let's add a trend line here and have it be exponential.
Yeah, because I did that just like messing with it, and
Mm-hmm.
I got R equals 1, and I got the same K value that you have.
0.011.
Yeah.
Yep. It works.
So like, is that something that you can do, or
Sure.
is it just better to stick to that?
No, I don't think there's anything wrong with doing it this way.
All right.
Because we get the same 0.01104. Excel is smarter than it used to be. So the reason why I wouldn't have done it in the past is like, see the shape that it's showing here of exponential? Just past versions of Excel would think it's got to be in like an exponential growth, where this is an exponential decay reaction. So that's kind of why I got in the habit of doing the heavy lifting myself and transforming it into something that's going to show itself as linear. But if you can arrive at the right answer a different way, then I'm all for it. Other questions? All right. Second order reactions. So how can we, like the whole point of this derivation is to tell us how we can go from the reaction rate to predicting amounts or predicting concentrations. So in second order reactions, the reaction rate is equal to some constant multiplied by the amount squared, or the concentration squared. So we take the integral of both sides. In the end, we end up with this this equation, which says that the concentration is the initial concentration divided by 1 plus K times T times the initial concentration. So the way that we linearize second order reactions is by 1 divided by the amount, and that'll tell us from the slope of the line what the magnitude of K is. But we have to keep in mind that in second order reactions, a production reaction would have a negative slope and vice versa. So let's try that out for this last question on the in-class exercise. The decay of nitrate into nitrite and oxygen is illustrated with the data provided below. So we've got time of concentration, and it's given that this is second order kinetics. So let's determine K and then predict how much of that would remain after 40 minutes of the reaction occurring. Let me create a new tab here. This is our second order kinetics. Okay, so let's put the data in. Time in minutes and concentration in milligrams per liter. (100, 90.91, 83.33, 76.92, 71.43, and 66.67. Okay, we're given outright this is second order kinetics, so that tells us we're going to need 1 divided by concentration. So we're going to do that as a column, 1 divided by concentration, and that's going to have units of liters per milligram. So it's going to have the inverse units. So equals the concentration, 1 divided by the concentration. There we go. And then we want to graph time on one axis and 1 over the concentration on the other. We'll insert a chart, scatter plot without the curves being added. And this is showing the slope is going upward, but we know the concentrations are going down, and that's just a function and a feature of second order kinetics, so we're not panicked about that. Let's add the axis titles so that we can remind ourselves on the horizontal axis here, it's time in terms of minutes, and in the vertical axis, this is 1 divided by concentration, and it has units of liters per milligram. All right, I'll get rid of the lines. I'm going to give this a new title as well. I'll call this second order kinetics. Let's add that trend line. Right click, add trend line, give it the equation and the r squared because we're curious. Maybe increase the label. Yeah, label options. Instead of general category, I'm going to get number, 5 digits, just to see it's exactly 0.0100. Okay, so K for this next one is 0.001. And so what will be, let's think about what's going to be the units of K. So we want it to be multiplied by time and concentration, and then it's going to be unitless after we do that. So it's got to have units of, for this one it was minutes as the time, milligrams was the mass, and liters. So it is 0.001 liters per minute milligram is the units there for the K value. And it's asking in the handout, predict the amount that will remain after 40 minutes. So we've got 5 minutes of data. We want to know how much will be present after 40 minutes. Here's the equation. So we want to know the concentration after 40 minutes is the initial concentration, which was 100 milligrams per liter, divided by 1 plus K, so 0.0010 liters per milligram, minute milligram. And then we're going to multiply that by the amount of time that we're talking about, 40 minutes. And then multiply that by the initial concentration that was present, 100 milligrams per liter. So how much will there be? After 40 minutes of decay, I think that we're going to have 20 milligrams per liter that remains. Any questions about second order kinetics? All right. So, with these, you should be able to get, I think, pretty far down the road, not only on the second homework assignment, but this is starting to go into material on the third homework assignment as well. Let's just briefly talk about one other thing related to kinetics, and that is half-life. So half-life is defined as the amount of time it takes for half of an initial substance quantity to decay. And it's talked about a lot of times in terms of nuclear materials, half-life. And we all kind of know that radioactivity lasts for a long time. And we define it as the amount of time it takes for the concentration at that time to be 0.5 times the initial concentration. So that means half the amount that was there at the beginning. So if you've got zero order kinetics, it's pretty easy to calculate the half-life just by the initial and the final concentration being half the amount. So for zero order kinetics, it's 0.5 times the initial concentration divided by the reaction constant K. Whereas for first order kinetics, it is 0.693 divided by the K value. And that 0.693 is just the result of the logarithm of 2. Because the logarithm of 2 is just the initial concentration divided by half the initial concentration. So nuclear material sometimes decays very slowly, and there's a lot of concern in environmental engineering about how nuclear material can be safely stored. And right now, the United States doesn't have a systematic way for storing spent nuclear fuel in a long-term manner. Like right now, most nuclear power plants just have cooling pools where, once the plutonium or uranium is spent, meaning it's exerted most of its energy, it still has a lot of radioactivity. Even after it's no longer commercially viable to extract energy from it, it's still radioactive and dangerous to people. So to avoid it from overheating and causing a chain reaction, they just put it in cooling ponds near the reactor itself. There's been a long-term study done for like 50 years or more. There's been a lot of research done at trying to provide for long-term nuclear storage in Nevada. There's this very stable geological formation called Yucca Mountain, where it was intended for them to drill into this mountain, and they could have 1,000 feet of rock above where the nuclear fuel would be stored and 1,000 feet below where the nuclear fuel would be stored until you got to the water table. And it was solid rock with very few fractures. And so they weren't just going to be like throwing the plutonium and uranium on the ground. Obviously, they were going to store it in sealed containers and keep careful watch over it. But this was thought to be a particularly safe place to bring all of the nuclear fuel together because it's under a mountain, and people with bad intentions aren't going to be able to get to it if it's under a mountain. It's generally safe from wildfire and tornadoes and earthquakes, like tsunamis. Like none of those things are going to affect nuclear fuel that's buried under a mountain. In the same way that right now nuclear fuel is spread out all across the country and is exposed to a variety of natural and human-derived threats. So they spent $9 billion studying this site, like doing all kinds of core samples of the rock to make sure that it was continuous and didn't have fractures, doing lots of different design plans, and ultimately they came up with a cost estimate of $55 billion, which is crazy. If you think basically what they were going to do is just dig tunnels into a mountain. But they really, I guess these were going to be really good tunnels because it was going to be $55 billion. It was going to have enough storage capacity to store 100 years of nuclear fuel. And then they assumed that it would need to be down there depending on like how spent the nuclear fuel is and where it came from and what type, anywhere between 10,000 years until it was no longer dangerous to people, up to 1 million years. And so that's the time frame they were looking is this mountain going to be stable for 1 million years? And you can see the design was that they were going to have a series of parallel tunnels, a couple of ways in and out that obviously would be really carefully controlled, but unfortunately, the plan never came to fruition. It was not approved by the Senate, largely because Nevada's senator at the time, Harry Reid, was opposed to storing nuclear fuel in his state. His constituents didn't want to have like uranium and plutonium coming in by truck, and this was only about 60 or 70 miles from Las Vegas, and so people whipped up a lot of panic about, oh, it's so close to an urban area. So it never got built, and so what we're stuck with now is just a lot of nuclear fuel sitting in poorly protected ponds in nuclear plants all across the country. I mean, poorly protected is relative. I mean, there's guards for sure, but it's not under 1,000 feet of rock like it ought to be. So where we're going from here is in class on Friday, we're going to talk about zero, first, and second order reactions inside of reactors. So it's not just the reaction that's happening, but it's also where it occurs that impacts how much time it will take for things to decay, or what the concentration is when the constituents come out of the place the reaction is happening. So we're going to be answering questions like, how big should a reactor be? What flow rate can go into the reactor? What temperature effects are there going to be? How much should we stir these reactors? And what effect is that going to have on the rate of the reaction? So we're going to talk about reactors in class on Friday. I'll see you then.